me. Cool, thank you. So finally, he's going to stay in his own lane for once. So, climate change in the U.S. Before I get started, let me mention I've talked to the Home Office in Colliersville, Tennessee. They said these are now on sale for the low, low price of $50. However, you can get yours free by going to the box out back and just picking one up and going off with it. So that's a $50 deal on sale for the same price that God started the world with. Let me first of all dispel with one of the questions. Why are you focusing only on the United States? And the answer is I've only got an hour to talk, so we've got to limit it to some extent. And the United States actually turns out is much more homogeneous, means it's all the same. And so as a result, we can diagnose things much easier. If we did Europe, for example, you've got all different countries, and they were involved in different wars over time. They do different gauges, they change them. Figuring out how that affects the record is far more complicated if we looked at Europe, for example, than it is in the United States. And besides, we are in the United States, so when in Rome, visit Rome. So in any event. Another question that often comes up is, how did you get involved in this? And I got involved in climate change because I was really interested in weather forecasting. And so early on, I went to the University of Maryland and the University of Delaware and walked in off the street and said, I want to talk to somebody about your program. I don't recommend doing that, but nevertheless, God led me to two people who changed my fortunes forever. They both said essentially the same thing. They were famous climatologists, and I had no idea at the time who they were. But they both said, look, weather forecasting is going to be done by computers. It'll be shift work. There's no excitement there. The big excitement over the next 50 years or over what will be your career, however it's going to be, is going to be climate change. And that's what you need to get into. See, what I knew then, but what you don't know now, is what they meant by climate change. What they meant by climate change was global cooling. Wait, what? Yeah, global cooling. Because you see, at the time, there was all sorts of discussion that the Earth was headed into the next ice age. End of the world feared with another ice age. Scientists agree world is cooler. Scientists ask why the world climate is changing. Major cooling could be ahead. This was all over the press. Now, how was that different than it is today, with the exception of a sign change? The answer is there wasn't a big environmental movement, and there wasn't a big social ability to communicate. I mean, when we communicated, we talked to each other. You had half hour of nightly news. You saw Walter Cronkite last time. That was the nightly news, and you got a half hour. All the news that could fit into there is what you got. We didn't have 24-hour news services that had to have stuff filled and had to sometimes make stuff up to fit into it. So there wasn't a big push, and so when Newsweek puts out a graph like this, people said, oh my goodness, the temperature was going up, but in 1940 it started to plummet. If this continues by some unbelievably far-off date, such as 2020, we could very well be in the middle of the next ice age. And we're not, because that didn't continue. That actually stopped somewhere about here and started up again. And now, of course, we're worried about global warming. What global cooling was supposed to do is create more storms, more floods, more droughts, more hurricanes, more tornadoes, more disasters. Of course, what global warming does is creates more floods, more droughts, more hurricanes, more tornadoes, more disasters. So any climate change apparently destroys the planet. That's not the way it works. By the way, so there were also books that you could buy on it, The Weather Conspiracy, The Coming of the New Ice Age. One I actually like is The Cooling by Lowell Ponty. It gets cited quite a bit. So there are lots of books available. We've tried to scrub some of them so people say, no, they didn't really exist. And no, there weren't scientists that believed that way. But my friend Tony Heller runs a YouTube site, and he does a lot of work pulling this stuff out and saying, gee, back in 1928, there was actually a report that ships sailed all the way to the North Pole without hitting any ice. And of course, we were told back in 1928, the world was freezing, and that ice has been depleting because of global warming. Well, how did that happen? So he documents that kind of stuff, and it's kind of fun. But we've moved on. We're no longer talking about global cooling. Now, of course, it's global warming. And as I said, global warming is potentially going to threaten the planet. Now, we've been talking quite a bit about the concern with environmental stewardship. And so if we are destroying the planet, it makes total sense that we do something about it. The question is, what do we do? And more importantly, looking at risk-reward and cost-benefit analysis, is there really something to worry about? Now, unlike most of the other presentations, you can disagree with me. Okay, in science, there is the availability of disagreement. And this topic is not going to affect your salvation, which is probably why we put it on Thursday. But in any event, it's not going to affect it. And if you disagree with me, that's fine. I've learned I have to have a very thick skin. I don't have one, but nevertheless, I pretend that I do. So that's fine. But as you know, we are worried about all sorts of things. And back then, there was the interest over geoengineering. Maybe we can stop this ice age. Maybe if we took a lot of soot, went up in the Arctic, and covered it over the ice pack, we could absorb more energy. We could start to change this global cooling around, stop the planet from heading to the next ice age. Well, we're doing the same thing now. The question is, can we actually change things then? And if I go back to my antithesis of the precautionary principle, we shouldn't be doing anything unless we can guarantee it will have a positive remedy and it doesn't create other problems. Think about it. If we had covered the Arctic in soot, where we'd be right now. So that's one of the issues. But you can see here, this is 4 months ago in January, 5 months ago. Oh, it's June now, 6 months ago. Should we block the sun to counter climate change? Block the sun? Really? How are we going to do that? And B, do you realize how much expense that's going to cause? And what happens if we do block the sun and we start to cool the planet? So geoengineering is one of those fun discussions, but it can be very expensive and it can be bad. One of the things, I think I talked with someone before, they said that every time it comes up, I don't know why, every time there's a hurricane, somebody says, why don't we just hit it with a nuclear bomb? And I've heard this since I started in the University of Oklahoma in 1988. I got a letter from somebody who said, we could stop these hurricanes, just nuke them. And I always thought about that. Well, first of all, what do you do with the fallout? Wow, take a big storm that's moving air all over the place, create lots of fallout, and then just have it distributed all over the place. But secondly, why would that work? A hurricane requires vertical motion. What does an explosion do? It causes air to rise. All you're going to do is fuel the thing. But as Roy Spencer clearly points out, here's the problem. You've got so much energy in a hurricane and so little energy in a nuclear explosion. It's like trying to stop a freight train by putting a fly in front of it. I mean, that's just not going to happen. And of course, we see all sorts of weird stuff. For example, this is Robert Reich. You may know who he is. The media's refusal to be honest about climate change is a threat to democracy. Now, what he means is not how they mislead you, it's that they're not doing enough. And that is a threat to democracy. My friend William Briggs writes some cool articles from time to time. Here's one. Every place on Earth is actually warming faster than every other place on Earth. If you think about that from a statistics standpoint, that is not physically possible. But he identifies all these places, too. And you can see with articles that you can cite, and when you figure it out, he's exactly right. At the end of the day, the media has told us that the entire world is warming faster than the rest of the world. And that's, again, not a problem. So what we really want to figure out is, in the time we have, what kind of questions are we able to look at? So in other words, is our climate really changing? And are we to blame for it? Because the last thing we want is to be standing idly by while disaster sneaks right up behind us. But on the other hand, we don't want to waste time and effort worrying about things that just aren't likely to happen. But more importantly, what we really need to know is what are the correct questions to ask? And as you can see the expression on the scientist's face, this isn't one of them. So what are the questions? So first of all, let's ask, what is the debate? We know that there's at least two sides of this, and there's many more. I don't want to give you the impression that there's people that agree and people that disagree. It's not the way it works. There's a whole spectrum of people believing a variety of things. So first of all, on what can we agree? Does most, not everybody, but what does most people agree? So the first thing we can agree upon is that our climate is changing because our climate has always changed. The phrase climate change is actually repetitively redundant. And besides that, it says the same thing over and over again. So climate changes because climate always has changed. The problem is we got into the idea of referring to climate as average weather. The one thing I hate is people say, climate is what you expect, weather is what you get. No, okay? Because climate itself is dynamic, it is variable, it is ever-changing. I could simply say, look, climate drives the background on which things can happen, and weather is just a random roll of the dice of what you get today. And meteorologists would be really upset with me, and probably rightfully so. So climate varies for a variety of reasons. Weather fluctuates for a variety of reasons. We're going to look at the climate end of the standpoint. And if we look historically, there are a number of reconstructions. This goes back, for example, 2,000 years. You can see the medieval warm period. You can see the little ice age. You can see the warming at the end. And, you know, the Vikings came into Greenland during warm periods, and the Vikings left during cold periods. So we see lots of variability in the record, and we do see trends over time. The question, of course, is why is that warming happening? Are we responsible for it, or is it just a natural cycle? The second thing we can agree upon is that humans can and do influence our climate. And we've talked about before, I guess we haven't talked about before, one of the things we can talk about is the urban heat island effect. If you think about any major city, if you happen to be around them and you're watching the evening news, look at the weather report, and particularly on a night where there's really nothing going on in weather. There's no fronts going through, that kind of stuff. You'll see that the warmest areas is downtown. The farther out you get, the colder it gets. And that's because the city retains the heat. There's lots of asphalt, there's lots of macadam, there's lots of black and dark surfaces to absorb energy. The surfaces retain the energy and then give it off later at night. So the urban area is going to be warmer. So as an urban area grows, we're going to see this growing urban heat island. Is that climate change? Well, of course it is. It's local climate change. So what we're trying to do is get a background effect to say, what is the global climate doing? Because locally, your climate can be affected by a variety of things, even down to the point as to what kind of crop do you put in the field or what color do you paint the top of your house. Third thing we can say is that carbon dioxide and other trace gases, including such things as methane and nitrous oxide, have increased, and they're increasing largely due to human activity. We have a measurement at Mauna Loa Observatory. The Mauna Loa Observatory actually is now closed, and they've moved it to Mauna Kea because this was located on an inactive volcano, which has now become active. If you know anything about volcanoes, they outgas lots of carbon dioxide, which makes it stupid to put this there. But in theory, we've put it in the middle of the ocean, so it's not affected by local features, except, of course, the active volcano. But you can see it's rising over time, and you can see sort of a sawtooth. That's the seasonal cycle. So as plants grow in the summer, actually carbon dioxide goes down because they use it, and in the winter, carbon dioxide goes back up. But we've got to be careful, because when we start to look at graphs, they can be misleading. You'll notice this does not go to zero. This looks like it went from almost nothing in 1959 to really high values. In fact, if I showed you the scale with zero, it looks really like this. And we look, the total change over the last 250 years has been 1/100th of a percent of the atmosphere. So it's the equivalent of 1 penny out of a $100 bill. The fourth thing we can agree upon is that globally air temperature has risen over the past century. People say, are we seeing global warming? Well, of course we are. The real question is, why are we seeing this warming? And so we saw here, right in here, you can see the temperature decrease from 1940s to 1970s. Oh my goodness, global cooling. We must do something about it. Now it's turned over and it's gone up here. We have the the little ice age. It's a misnomer. It wasn't an ice age. It should have been a little cold period, but that doesn't have the same cachet. In any event, we've got that in blue. We've got this in red, blue. Ooh, it's something bad's happening. So the temperature is rising. The question, of course, is why? So the real debate is, to what extent are humans responsible for the recent climate change we see? What are the future consequences of climate change, both natural and, big word, anthropogenic, just a fancy word for human-induced, but I like to impress you. Number 3, what should our response strategies be? And I always argue that a well-informed and prudent response is always the only course of action. So let's go back to our global air temperature trend. There was something in here that you probably missed, and that is, this is from the Climate Research Unit at the University of East Anglia. They are very much concerned about global warming, but if you look at their own reconstruction, the last 8 years have not seen warming. Have we headed into a position where this goes down? Sorry, can't do it off the board. How does that do when the temperature goes down? I don't know. Could be. Some solar physicists are saying the sun has actually reached peak output and that it's actually starting to decrease. As my friend Willie Soon says, it's the sun, stupid. But as Roy Spencer says, it's natural variability. So there's even people in this camp that says it's not human-induced that disagree on why it's happening. So I don't want to give you the impression that I have all the answers. Science never has all the answers. Surprise, surprise. So the idea is we need to look closely, and here you can see, even by their own admission, it's not changing. Now, the interesting thing is, if I were giving this presentation from an alarmist perspective, I would start with this curve and say carbon dioxide is rising. Carbon dioxide leads to increased temperatures. Then I would put carbon dioxide curve over top the air temperature curve and show you that air temperature follows carbon dioxide perfectly, and therefore declare that carbon dioxide is in fact the climate control knob. And see, isn't that proof? The problem is in statistics, correlation does not prove causality. So just because those two curves go together does not necessarily mean that one's causing the other. In fact, historically, if we go back in what we think is the long-term record that they're trying to reproduce ice cores, and most people that are in this are long Earth evolutionists, their concept even shows that the temperature actually leads, the carbon dioxide signal follows. And that's the way they see it from their perspective. But they don't tell you that because they don't think it works here. Because if this were temperature driven, then that would be against the way it works. So we asked the question, is air temperature changing, and if so, how? And my answer is, certainly it's changing. We know very well, for example, this is Washington, D.C. I hope you don't have to go there. But in any event, the idea is we used to have our observations right downtown here. Well, the urban heat island says our temperature is about 85 Fahrenheit downtown. It's about 77 Fahrenheit around the edge. So it's warming by, on average, let's say, about 8 degrees Fahrenheit. So we had our stations located downtown. Meteorologists should be downtown where all the action's happening, so therefore we'll put it downtown. Then in the 1940s, what happened? We came up with these newfangled things called airplanes. And it turns out airplanes need to know a little bit about the weather. So wouldn't it make sense to move our stations from downtown to these airports, as we would call them? So yeah, so we create Dulles Airport, which is out here in Virginia, and we move all the stations out here. So what do you think happens in 1940s? Temperature goes down. What happened in 1940? Temperature started downwards. So that continues. Well, what has happened to D.C.? If you know anything about D.C., almost everything in here is highly urbanized now, and even more so, outside the box. So Dulles is now surrounded by an urban area, and so over time, Dulles Airport has seen an urban heat island growth. So what do we expect happen? It catches up to it at about 1970, and then the temperature starts again. So one of the things we have to do is separate stations which are affected by the urban heat island from stations which have been out literally in the middle of nowhere, God's country, so that they aren't affected by this urban heat island effect. Because what we generally see in rural stations is a warming, a little bit of cooling and warming again. But the urban subset has a warming built into it that's because of the growth of the city. So what we do is select only these stations. And the National Oceanic and Atmospheric Administration has done just that. And they started keeping them very clean, taking care of them in 1990 so we can plot the data. So here are the data from those clean rural stations over the last 30, 32 years. Now, when I show this, most of my graphs, this is going to be time. So we've 1990 over here and 2020 is over here. Temperature goes from -6 Fahrenheit to 8 Fahrenheit. So that's a range of 14 degrees Fahrenheit. And you can see we've removed the seasonal cycle, lots of variability. Has there been any trend over time? Is this curve going up, as you would expect with global warming? Would it be going down with respect to global cooling? Or has there been virtually no change whatsoever? There's been virtually no change whatsoever. Now, so we've seen that in the media. Oh no, that's right, we haven't seen that in the media. So the idea is once you sort of look at rural stations, there's lots of variability, but there's no long-term trend. Well, frankly, nothing responds to mean global temperature. It's always the extremes that kill the most people and create the most economic impact. So we really want to focus on those. So maybe it's not average temperature, maybe it's the extremes. So in particular, climate change we see is increasing the frequency and intensity of extreme heat waves. Hot temperatures are becoming more frequent. In fact, summer in America is becoming hotter, longer, and yes, indeed, more dangerous. Except it's not. This is data again from the National Oceanic and Atmospheric Administration. We have 682 clean stations. When you see things like USHCN, these are stations in the middle of nowhere. They have more than 105 years of record. So this is 1895 all the way out to 2015. Actually, the record runs to 2018, so it's a little bit farther. This is days with air temperatures above 100 Fahrenheit, which are the big ones, and 105 Fahrenheit, which are the darker ones inside here. What sticks out? Wow, these big ones here. That was in the 1930s. What happened in the 1930s? Yeah, the Dust Bowl. So very high temperatures, particularly in the Dust Bowl region. You would expect that in dry conditions. So we had lots of days with more than 100 Fahrenheit. We had a lot of days with more than 105. You can see the droughts of the 1950s. You can see 1980, which I remember quite a bit because I was working as a commercial plumber at the time. You can see over here the high temperatures of 2011 and 2012. Lots of variability. But is there a long-term trend? Are we seeing more conditions of 100 or 105? No. The record just simply doesn't show that. We can go back to NOAA's record that we just saw a moment ago. We can look at long-term trends there. Again, lots of variability, but no long-term trend. Well, maybe it's not temperature that's the real big issue. Maybe it's wildfires. That does a lot of things, and we can see climate change is causing more wildfires, and governments are unprepared, says the United Nations. And if the United Nations says it, it simply must be true, except it's not. Generally, what you see is the biggest fires occurred in the early part of the century. Why would that happen? Well, think about it for a moment. What did we not have back here? Satellites, airplanes, helicopters. We couldn't move people around easily to get them to fight fires. We couldn't see the fire developing and where we needed to be. We couldn't effectively get people to where they need to be. We couldn't put the fire out from the air. We just didn't have that capability. So when fires started, they tended to burn out of control. Then we started to see down values, and it got less. And then we started to say, well, we've got to protect old growth forests. We've got to leave forests in their native conditions. And what that did was create a lot of dead and decaying material, which dried out and therefore became the potential for fires. Usually what they will show you is they will cut this off in 1980 and say, see how it's increasing? But you've always got to go back and look at the longer record. And as I said, this is not data that I've made up. This is actually data from the U.S. Forest Service. Well, maybe it's snowstorms. Snowstorms are fun because if we get warmer temperatures, we can actually get more snow. But if we get warmer temperatures, we can actually get less snow. So they've got both ends of the spectrum covered. And I remember, I didn't put it in here, but there was an article in one of the UK magazines that said, by 2010, the United Kingdom will not ever see snow again. They've seen snow last year. But in any event, that's the concern. So the question is snow becoming less frequent or more frequent? And I'm going to look a little larger scale here. This is Northern Hemisphere showing to you in blue. So Northern Hemisphere is in black. The Eurasia is going to be in red, and in blue is going to be North America. North America, you can see lots of variability, but really there's no long-term change. And this goes from 1970 all the way out through current conditions. Eurasia is going to do something weird. It's going to start fairly high, and then in the 1990s, it's going to plummet. And then it comes back a little bit, and then flattens off again. Any idea what happened in the 1990s? What is the big portion of Eurasia that's going to have snow cover? Russia. What happened in the 1990s? The Soviet Union and satellite states all collapsed. What happened to our observational network? Gone. So we don't have observations anymore. That shows up in the record by showing an area decrease. Some of them came back, not all of them. So it comes back here and it flattens off again. So generally what we're not seeing is the hemisphere becoming more snow covered because warmer conditions can get you more moisture in the air, which could give you more snow. We're not seeing less snow going away because warmer conditions melt off snow. In fact, if it was global warming driving this, this probably would decrease because at the margins of the area we'd have warmer temperatures and not enough to have snow cover. Well, maybe it's not snow. Maybe it's super hurricanes. And I can show you, like I said, till noon, articles in the media telling you this. Climate change is rapidly fueling super hurricanes. Hurricane Irma's epic size is being fueled by global warming. So what do we see? Let's go to NOAA. Let's look at the data. This is data from 1970 to 22, so we got 50 years. You can see in this case tropical storms and hurricanes. Hurricane is simply a tropical storm that has an intensity, sustained intensity of more than 72 miles an hour. And you can see lots of variability, no long-term trend. In fact, if we look at 2022, you can see over the last 50 years there have been only 2 periods where we had fewer hurricanes than in 2022. Where did you see that in the media? You didn't. But data from NOAA globally shows that. Well, maybe it's not number. Maybe it's intensity, because that's what the other thing just said. Maybe we're getting more major hurricanes. So here is our all hurricanes up here from the previous graph. Here are the major hurricanes. And in fact, you can see that over the last 50 years, this goes from 1980 to 22, you can see that only once have we had the number of major hurricanes be that low. Again, that's not reported in the media. And I didn't show it, but we can go back in time. If you go back to 1933, which was 90 years ago, there were an exceedingly large number of hurricanes. We were told that never happened. Of course it did. There was the 1935 hurricane went up the coast. It's the only hurricane we know that hit every state on the seaboard with hurricane-force winds. 1938, we lost, I can't remember off the top of my head, I think it was like 5 billion board feet of lumber in the Northeast due to hurricanes. We've had major hurricanes and devastating hurricanes all the time, so they're not getting more intense. Well, maybe it's the energy, and we measure that with something called the accumulated cyclone energy, or the ACE index. We can plot that over the last 50 years, and you can see there's lots of variability. There was a lot of energy tied up in hurricanes in the 1990s. There were a lot of major hurricanes then. But nevertheless, lots of variability, no long-term trend. And that's going to be the key thing, is that we're going to see that climate varies a lot from year to year. But we rarely see trends. And the reason I just changed that from never to rarely is because the next slide, there is a trend. This slide goes from 1945 to 2020. It is in black, the North Atlantic and Western Pacific basins, which account for about 70%. The number of hurricanes making landfall has actually decreased. Not increased, decreased. Now, technically, that's what you would really expect true from a warmer world, that hurricanes would become slightly less intense, slightly less likely to make landfall. We're seeing that. I'm not sure statistically I would make a big deal of it, but I will say it's going in the opposite direction of everything we've always been told. Well, maybe it's not hurricanes, maybe it's tornadoes. And I personally can say that I have been touched by tornadoes. I used to own a house in Oklahoma. I fortunately sold it. 7 years later, it was hit by a tornado. I owned a house in northern Delaware. It was missed by a tornado on August 4th, 2020 by 150 feet. I just built a house in southern Delaware this past April 1st, April Fool's Day. A tornado missed the house by about 5,000 feet. Somebody referred to me as the human trailer park. The take home is do not live near me. But the question is, are they becoming more frequent, or am I the human trailer park? And now we have an increasing trend. Here we have 1952, here we have 2022, and we can see there is a trend going on. So more tornadoes. Except there's something hidden in here you may not be aware of. What happened in 1990s? Fall of the Soviet Union. Yeah, but this is the United States, so that's not that answer this time. The National Weather Service modernized. And one of the things they did is they brought in Doppler weather radar. Doppler radar is good because it allows you to see winds. So we can see tornadoes that we may have missed before. So if a tornado happens at night in a remote Kansas wheat field, we can see it where we may not have been able to see it in the 1940s or 50s. So if we divide this into the pre-weather radar series and the post-weather radar series, what you see is actually we can see more, but there really isn't a trend. This was effectively flat. This is effectively flat. And the change in the mean value is because we're just better able to see them. Well, the definitive question is going to be, let's go to the big storms. EF 2, 3, 4, and 5. What do they look like over time? Because we won't need Doppler weather radar to see them. We would have been able to pick them up whether we had radar or not. And if we look at those, they're actually decreasing. Now, that's what you would expect in a warmer world. What gets us a tornado outbreak? You have cold, dry air coming out of Canada. You have warm, moist air coming from the Gulf. These two extremes collide. What happens under a warmer world? The tropics warm a little bit. The poles warm considerably. So we decrease that pole to equator temperature gradient. We decrease the difference in those two outputs. And so as a result, storminess should decrease. And that's exactly what we're seeing. Well, maybe it's more floods. Maybe it's more droughts. Or maybe it is more floods. Are we seeing more of those? And as somebody likes to call it, weather whiplash. You get a flood, then you get a drought, then you get another flood again. It's back and forth, back and forth. Are we seeing more of those? I think we are. And is it human-induced? I think it is. But I don't think it has anything to do with climate. Here's why. This is Tallyville, Delaware. Most of you have never heard of it, never been there. It's a suburb of Wilmington, which you've probably never heard of either because it's not Wilmington, North Carolina, it's Wilmington, Delaware, which is a small town outside of Philadelphia, which hopefully you've heard of. So this is 1937. So what does Tallyville look like? Well, this is US 202. Well, it would just become US 202, and it's still a dirt road. You've got lots of trees, you've got lots of farmland. It's rural. Trust me, it's not now. And I'm going to put this in motion. So what you're going to see is Tallyville change. So what happens when it rains in Tallyville in 1937? The water hits the ground, it soaks in. It takes a while to make it to the Brandywine Creek. What happens now in the year 2022? It hits the ground, and we've replaced all that ground with asphalt, macadam, roads, parking lots, buildings, and we get what we call street flooding. And so the water makes its way to the Brandywine Creek very rapidly and very efficiently. So we exacerbate flooding events. What do we actually do now? If you ever look at new housing construction, they're putting in a new housing development somewhere. What's the first thing they do? Retention pond. Why? To stop this from happening. This was all happened in the 1970s. You're not going to see retention ponds because back then they didn't realize. And there's no way now to put them in there. You can't do eminent domain, take your house to create a water pond. That's not going to happen. So nowadays we can accommodate this, but we didn't back then, and that's why they get street flooding. On the other hand, what about droughts? Well, water runs low. Out here, there's not that many people demanding water. There's not many water-intensive activities. 2022, you've got a lot of people needing that limited resource. It's not going to go nearly as far. So we're going to see more floods because of street flooding. We're going to see more droughts because there's more people in the landscape demanding water, more water-intensive activities. It's human-induced because we didn't get from here to here without human action. But it has nothing to do with climate. And how can I say that? Because NOAA runs something called the Palmer Drought Severity Index. And it keeps track of climate variability irrespective of what goes on the land surface. So it's simply a water budget accounting that takes into account how much rain do you have, how much evaporation do we expect to get from the surface based upon temperature, and it doesn't matter how you treat the surface. And so we can look at that, and this goes all the way back to January of 1895, all the way up to February of this year, and you can see lots of variability. You can see the droughts of the 1950s and how significant they were on the United States. Lots of variability, no long-term trend. The other side tells us how wet it's going to be. And so we can see here lots of variability as well, but there's no long-term trend either. Well, maybe it's extreme rainfall. We're told that rainfall events more than 4 times more likely in the next 50 years, it says, and the heavy rainfall events of one day are becoming more intense. And they show you a graph that looks something like this, and we can see from 1910, a little bit of drop, and then we go all the way out, and in 1990, it starts to shoot upwards. If I update that with the current data, it's still there. And I'm going to plot a second-degree polynomial in blue, which, if that means nothing to you, ignore what I just said. In any event, from 1910 to current conditions, you can see a nice trend. So does that mean we're getting more rainfall? It's rainfall when it falls is becoming heavier. Well, what happened? Remember I said 1990, National Weather Service modernized. Another thing they did, in addition to weather radar, was to change the way we measure precipitation. Before then, it was all done by hand. We have a rain gauge sitting at a height of 5.5 feet. Why is it 5.5 feet? So that I can get to it easily, because I don't want to have to bend over if I'm working for the National Weather Service. So we put it up high. We literally open the thing up. We take a stick. We figure out how much water is in it. We empty it. This is done every hour. At some point, somebody said, why can't we automate this? And we certainly could. So we got rid of this whole concept and went to the automated surface observing system, which is now way down at the surface where the wind is lower. We have now a green thing around here, which is a wind shield. Wind decreases the catch. So if you put it lower to the ground and you put a wind shield around it, the catch becomes greater. It's a more efficient gauge design. So from 92 to 95, we've changed from a less efficient measuring gauge to a more efficient measuring gauge. So if I go back here and I color in red the pre-modernization and I color in blue the post-National Weather Service modernization, you see no long-term trend, transition, no long-term trend. So what we're really seeing in that record is not climate change. We're seeing a change in the way we measure from the instruments. When you put it all together, the total weather-related disaster losses as a percent of global GDP from 1990 to 2022, that curve is slightly downward. Statistically, I'm not going to say it's significant, but it's certainly not upward. We're not seeing more disasters that are killing more people and creating more economic distress. In fact, we're seeing less. So, where do all of these alarmist figures come from? It's not really that we're making them up, although you'll see in a minute we really are. They're called climate models. So what's a climate model? Back in the 80s, I used to have a copy of the climate model sitting on my desk. I don't know why I had it on my desk, because it just magically appeared there one day. It was this thick, about 50,000 lines of code. Nowadays, if I printed it out, it would be at least this high. Okay, it is very complicated. It takes everything that we know about the climate system, puts it into mathematical form, then you fire up the computer and you run it, and the computer, you hit it with a change in carbon dioxide, and you see what it tells you. We know, for example, that climate models always run hot. Here, for example, is a plot of 40 climate model runs. CMIP6 is just the composite model intercomparison project number 6. So these are a whole bunch of models that they get together and run at one time. The black curve is the satellite record from the University of Alabama at Huntsville. And you can see that most of these start to create much more warming than we actually see. In particular, I like this graph. This is the Intergovernmental Panel on Climate Change model simulations. There was 102 of them. This is the upper tropospheric temperature, so this is the upper portion of the atmosphere in which we see weather. We can see the average temperature is an increase of about 3/4 of a degree Fahrenheit per decade. That's the consensus from the model. What are the observations? They're actually about 1/3 of that. So the models always show more warming. So the question is why? Now, if you remember back to your class on nonlinear partial differential equations, well, actually you don't need to get that detailed in the model. It's actually really simple. And again, it's a simple equation. So the change in temperature in the model over time, change in capital T over time, small t. So that change, the model sees, which is what you saw in the previous graph, is driven by two things. One, how sensitive the model is to changes in carbon dioxide, how fast it's going to change the temperature as you change carbon dioxide, and secondly, how fast we change carbon dioxide over time. How do we think carbon dioxide is going to, what it's going to look like in 2100? Because if I'm going to forecast out, I need to know how much are we going to have in the atmosphere. The concern is these two numbers are grossly overestimated, which is why that number is overestimated, which is why the previous graph always shoots upward relative to the observations. The first term is generally called climate sensitivity. How sensitive is the model to changes in carbon dioxide? Everybody, except those of us on the inside, always thought that the way this worked is we took all of the physics that we know, we put it into the model, and the model decides what the impact of carbon dioxide is. That's not how it's done. In an article written in 2017 in the Bulletin of the American Meteorological Society, the modelers finally came clean. And they said the way it's done is we tell the model what to do. It's a tunable parameter. If we want to have a model that is completely unresponsive to carbon dioxide, all we do is say the climate sensitivity is 0. And the model does that. We tell it what the carbon dioxide response is going to be. The model doesn't tell us that. So what do we tell it? Well, there's a lot of ways of estimating the climate sensitivity from other means. Generally, what we've seen over time is our estimate of how sensitive the climate is to carbon dioxide have been decreasing. The models, however, keep using high values. That's one reason why they always overstate the case. They are too sensitive to carbon dioxide relative to what we know. The other term is how fast do you think carbon dioxide is going to change? And we have a number of scenarios. For example, we have possible futures. These are 5 different emission scenarios. You'll notice one is labeled highly unlikely. unlikely, and these are more likely. In fact, this is likely, and this is probably unlikely as well, because we're not certainly going to follow Paris, even if we say we are. So which one of these do we use? If you've been listening before, you know exactly which one we're going to use. We're going to use the highly unlikely one. My job at the White House, at the U.S. Global Change Research Program, was to make certain that the next national assessment did not use that scenario and instead used one down here that was far more likely. For that, I was there 9 weeks, of which one was Christmas, one was New Year's, one was Thanksgiving, one was the last week when I went back, and one was there was a national meeting, so we didn't meet. So I was there for 9 weeks, of which five of them we were on vacation. I was there 4 weeks, and for trying to do this, I got charged with violation of White House rules. Essentially, I did things under the White House auspice that I wasn't supposed to do, which was to try to make science correct. For that, I was charged with, they wanted to, if convicted, he will be guilty, he'll be charged with 5 years imprisonment and $5 million in fine. I remember Rachel Maddow on MSNBC saying, I hope they, well, I can't tell you what she said because this is a polite company, but she did say, I hope they put him in jail. No, they're not watching me where I am. It's all bravado. In fact, in the article down at the bottom, they said, a spokesman for the White House and someone on the outside that knows says he was told, you know, this was his job assigned by the White House. Okay, then what's the whole article here about? Anyway, so we always use that scenario. The previous slides I showed was the scenario we should be using. So here is what we saw before. This is using a correct, at least, change of what we think is reasonable over time, projecting what I showed you out last time to 2100. But as I said, we don't use that scenario. You always see the unlikely scenario. So in fact, this is the one you're usually shown. What do we see? By 2100, temperature rise is going to be about 10 degrees Fahrenheit. Are you worried now? Well, if we look at the observations, we know that it's probably going to be somewhere down here, if we can assume things will continue and not change. So the models overstate the case, and they lie to you. So in the remaining time I have left, let me explain to you why I don't believe carbon dioxide is in fact the climate control knob. And it's actually simple. You don't need partial differential equations to understand this. The most important greenhouse gas, carbon dioxide, water vapor. Water vapor absorbs more energy, and I've talked about it before, but I'll keep saying it. Water is probably the most beautiful gas, beautiful compound that God ever created. It does all sorts of things with climate, and in particular, it moderates it. It is the most important greenhouse gas. It waters the earth. We need water to live, but it changes form. It creates clouds. There is a feedback, essentially, which says it's the infrared iris idea, that when we get a warmer, the world starts to warm, we get more high clouds, which reflect off sunlight, which cools the temperature. And when the temperature goes down, we stop getting convection, so we don't get as many clouds. Clouds go away, more sunlight comes down, and we warm the surface. They are regulating mechanisms, and water is everywhere. But, and I can show you this in numbers, I'll show you in people pulling on a tug. We've got surface radiation coming off, energy going to space. We've got evaporating water. We've got air being forced to move around by moving air. We've got energy coming in from the atmosphere. We've got energy coming in from the sun. And then we add more carbon dioxide, and there he is. That's all carbon dioxide adds to this equation, is a little teeny guy pulling out there at the end. That's all there is. The real proof, though, I think, is we need some fingerprint to say, what does warming from carbon dioxide look like? After all, if you're going to be a detective and figure out who done it, did carbon dioxide do it? is carbon dioxide responsible? We need to know what carbon dioxide does specifically. Every model says the same thing. That is that we need to be in the tropics, and that makes sense because where is the most outgoing heat coming from? The warmest place on the planet. Where's the warmest place on the planet? The tropics. So this should be in the tropics. And down in here, we have molecules that are absorbing as much as they could. It's the molecules up here that don't quite get as much heat. So if we have a little bit more heat going into the system, they will be absorbing more. The biggest signal from carbon dioxide, therefore, is going to be the upper troposphere. Remember, the troposphere is just a fancy word for the level in which we have weather. So the upper portion of the level, think about the top of the clouds, warming there in the tropics. And that warming should be 2.5 times what it is the surface. That's your fingerprint. If it's carbon dioxide, you're going to see that. And as I said, virtually every model does the same. They do it to different extents, but it's still about 2.5 times. It's still over the tropics, and it's still in the upper portion of the tropical troposphere. So let's look at data and see what happens. So here you have it. Data measured by the UK's Hadley Center. You can see temperature trend between 1979 and 2006 for the tropics, 20 north, 20 south. And if I blow it up, you can see here is the carbon dioxide signal in the upper troposphere. So there it is. Yes, carbon dioxide is responsible for warming. However, remember, that was to be 2.5 times what it is at the surface. So if I did this at the surface, this has to be down about 0.03. It's not. It's much larger than that. So there's somebody warming the surface. Carbon dioxide is doing a little bit of this, but there's somebody doing a whole lot more. And remember, we're really interested in the surface because where do you live? You don't live up here. You live right down here at the surface. So surface warming is coming a little bit from carbon dioxide. But there's something else that's responsible. What is that something else? Well, let's look at daytime versus nighttime. What happens at night? The surface cools. Cold air is more dense than warm air, so cold air stays down at the bottom, warm air up above. That's a stable layer. If you ever see, usually early morning, you go out as you're getting on a bus to go to school or you're getting in a car or something, you get cold air at the surface, you get a layer at the bottom of fog. And then usually you can see, so you see people walking through the fog, and it looks like they're ghosts floating because you can't see their legs moving, but you can see their bodies moving. It looks weird. Well, that's what's happening because it's separated. So here, the upper air is separated from the lower surface. This is affected by changes in buildings, farmland, and things that are happening at the surface. So this would be, if we see warming at night, is going to be a land use effect. Daytime, you're getting a lot of mixing. The surface warms, the atmosphere heats the surface. We get a lot of mixing. Now the carbon dioxide and the greenhouse gases are all put together, all intermixed, and that would therefore be warming that would be responsible from greenhouse gases. So if we see daytime warming, it's carbon dioxide. If we see nighttime warming, it's land use. Now all we have to do is look at some data. So here we have data from NOAA. This goes from 1910 to 2015, the percent of the area of the United States affected by extremely warm minimum and maximum air temperature in summer. Focus on summer because that's where this difference is going to be the biggest. And what do we see? Here's extremely warm overnight lows, and they're increasing. So the trend is for warmer nights. The other one is extremely warm daytime highs. And what do we see? No trend in daytime highs. There's no fluctuation there at all. The other side of the equation is cool minimum and maximum temperature in the summer. So the first one is extremely cool overnight lows. We see that decreasing. So the trend is for less cooler nights. Extremely cool daytime highs, we see no trend. So there's no trend in the daytime. There's a trend at night. Who was responsible for the nighttime signal? Land use. Is it human-induced? Well, yeah, we didn't get cities by magic. So it's human-induced, but it's not carbon dioxide. And so anything we attempt to do with carbon dioxide isn't going to solve the problem because carbon dioxide is only a minor player. But carbon dioxide actually has a beneficial effect. It's plant food. This lady, Ms. Janine Benyus, she was the Rachel Carson Environmental Ethics Award winner. If you know who Rachel Carson is, you wonder how her name can possibly be associated with environmental ethics, but that says that she is actually on the other side of the environmental cycle. She said, organisms don't think of CO2 as poison, they think of them as a building block. And that's correct. Go into any commercial greenhouse and what do you see? You'll see a box like this. What's it do? It pumps in carbon dioxide. It creates carbon dioxide. Why? Because more carbon dioxide does two things. One, it makes plants grow faster. And if you're running a greenhouse, that's what you want to hear. The second thing it does is it makes them more water efficient. How does the plant get carbon dioxide and water? Through the stomates. So if you open the stomates, carbon dioxide can get in easier. Well, if you've got a higher concentration of carbon dioxide, the stomates don't have to open as much, and so the water loss becomes decreased. So not only do they grow faster, they grow more efficiently. This is Sherwood Itso. He was at the University of Arizona. He did some cool studies. He took a seedling and grew it for a time. This is just outside, so ambient CO2 at 350 parts per million. And by the time he took the pictures, that one had grown to about belt height. He grew one indoors with 150 parts per million enhanced, so to 500 parts per million, even more than we're now. And you can see at the same time period, it's grown up here to his chest. At 300 parts per million, it's now up to his neck. And at an additional 450 parts per million, so total 800 parts per million, it's now growing above his head. Plants simply grow better. If that's the case, shouldn't we see more green area on the planet? I mean, we've got plants outside. If we've got more carbon dioxide, shouldn't the place be greening? Well, it should, and it is. This is a change in leaf area from 82 to 2015, except in areas where we have obvious deforestation, in areas where we have urbanization taking place, and except in areas where we're in an obvious desert, Sahara Desert, for example, Antarctica, which is a desert. The rest of the planet is greening. More carbon dioxide is actually a good thing. As Sylvan Whitwer said, he's the head of the director of the Agriculture Experiment Station at Michigan State, the rising level of atmospheric CO2 could be the one natural resource that is progressively increasing food production and total biological output in a world of otherwise diminishing natural resources of land, water, energy, minerals, and fertilizer. The effects know no boundaries, and both developing and developed countries are and will be sharing equally. As President Jimmy Carter argued, the path to global peace is to raise the standard of living of millions of rural people who live in poverty by increasing agricultural productivity. Thriving agriculture is the engine that fuels broader economic growth and development, which would pave the way for prosperity and peace. More carbon dioxide in the atmosphere will do that. The last thing we're told is that the oceans are dying because carbon dioxide is killing them. As Jane Lubchenco said in her testimony in 2009, you get osteoporosis of the sea, which is the degradation of such things as lobsters and crabs. And she showed a picture like this where you take an organism and you see how that diminishes over time. Do you know how they got these? They immersed them in hydrochloric acid. The oceans are not becoming tainted with hydrochloric acid, and not all acids are the same. So what we have to do is think about what is happening in the atmosphere or in the oceans with respect to more carbon dioxide. You get, therefore, an acid called carbonic acid. And I'll bet that half of the room probably at some point today will intake carbonic acid because we know it as carbonated water. So if you're going to do this right, what you want to do is bubble carbonated water into a tank and see how life thrives. And as we said, or she said, lobsters aren't going to make it. Except if you don't use hydrochloric acid and you actually use carbonic acid, they grow. That's not to say you should drink carbonated beverages. What's happening is the additional carbon is being used by the phytoplankton. to grow. In turn, the zooplankton feed on the phytoplankton. The animals that feed on the zooplankton grow. And as everything grows up the food chain, so does the big predator at the end, in this case, the apex predator, which is the lobster. I'm from Delaware. We love the blue crab, and so crabs do exactly the same thing. More carbon dioxide, they grow bigger. It's happened in the past. You probably don't know them. How many people have ever heard of Trofim Lysenko? A handful of people have. Trofim was a Russian peasant, and he came up with a really cool idea. And I've been talking about agriculture with somebody, I can't find them right now, but you're going to love this. He came up with the idea that if you take seeds and you put them in a freezer and you let them sit there for a while, when you finally plant those seeds, the plants that grow, in fact, are going to be resilient to cold temperatures. It's environmental determinism. And when he presented this to Stalin, Stalin thought this was the greatest thing ever. Here is a peasant that's come up with information that even scientists don't know. And in particular, the whole area of genetics was just becoming, it was being developed by Mendel, who was a Jew, but more importantly, he wasn't a Soviet. And so what the Soviet Politburo said is, thou shalt not study genetics. And so as a result, anybody studying genetics was ousted, persecuted, in some cases killed. The whole concept of genetics went offline in the Soviet Union in the early 30s. Now, if you know anything about genetics, it's how most of common agriculture is developed. So what happened in the Soviet Union? Agriculture fell behind and fell behind and fell behind. And finally, when they ousted Khrushchev in 1964 and Brezhnev came in, he said, okay, this isn't working. You can go back and study genetics now. And so it was all over. I'm afraid that what this is going to take is finally a whole cohort of people, scientists that are in there now, to go away, and a new group to come up to finally say, wait a minute, this is madness. Let's look at this from a more reasonable standpoint. And so therefore, I usually conclude all my talks with, the debate is not about the science, and it never was. So the question then that raises is, what's it about? And I'll leave that for tomorrow. Now, if you want more information, I'll shamelessly plug, it's not my book, but it's a book I worked on. It's not out there, and I don't get royalties, so I'm not doing this to make money. But Fred Singer he's deceased, was a great scientist. He spent a lot of time in the federal government. So this is a book that talks not just about the politics, but about the science. And it's available from Cornwall. The Independent Institute published it. And as I said, it's not my book because it says with Legates and Lupo. As he said, he was 93 trying to finish it up before he died. We made sure that what was transcribed made sense physically, scientifically, and did some research for him. So that's why our name appears on there. Now at this point, I'm almost done, but I am just about that far away from heresy, because this would be the first talk ever given at the BWSC, I think, that never mentioned the Bible. And I can't let that happen. So, if you'll turn in your Bibles to Ecclesiastes 1. And no, it's not the verse on vanity is vanities, all is vanity. Ecclesiastes 1, verses 5 to 7 and verse 9. The sun rises and the sun sets, and hurrying to its place, it rises there again. Blowing towards the south, then turning towards the north, the wind continues swirling along, and on its circular courses the wind returns. All the rivers flow into the sea, and yet the sea is not full. To the place where the rivers flow, there they flow again. What has been is what will be, and what has been done, it is what will be done. There is nothing new under the sun. So you can see that the author of Ecclesiastes was also a climate scientist. Other books you can find on the Cornwall Alliance website, and I'll tell you tomorrow how all this came to be. Thanks very much.